Okay, we're going to go ahead and get started. So welcome. Today I'm talking about how Amplify optimized our incremental models using DBT, obviously, that's why we're all here, and Snowflake. And I do want to call out that we are using Snowflake, so some of what I say will probably be applicable to other data platforms as well, but some of it may be specific to Snowflake. So just something to keep in mind. I'm Dina. I'm a senior analytics engineer at Amplify. Amplify is an educational technology company. We create a bunch of online curriculum and assessment products, including the 6 that you see here. And I want to start with just like sort of setting the context, setting the stage for you. So talking about our big data. So we have some fairly big data. It's not enormous, but some fairly big data. Our largest DBT model contains currently 35 billion rows, and it adds about 100 million rows a day. It needs to be updated 9 times a day in order to meet reporting needs. This actually feeds back into some customer-facing data that we surface for them. And if we were to fully refresh that every time, I did the math on that, that would be nearly $3 million annually to build this one model. So obviously we're not going to do that. So we said, okay, well, we'll make it incremental. And we made it incremental using what we thought were best practices. And it turns out that making it incremental was a good start. But with data this big, that actually doesn't solve all of your problems. And specifically, I want to call out 3 problems that remained even after we made this incremental. So first of all, we had to use the same Snowflake warehouse size for both incremental loads and full refreshes. And I'll talk more about that in a bit. The second thing is that we were like, okay, so we're supposed to add unique tests to our primary keys, right? Except you have 35 billion rows, and even though you're building it incrementally, it's going to check all 35 billion rows for uniqueness every time, and that is just not feasible. And then finally, this model was still costing $50,000 a year to build. So, obviously, that's not a huge amount of money, but you have 20 such models, and now that's $1 million, and that's before anyone has even run a query against them. So in today's talk, I'm going to focus on how we solve these problems, and I actually want to start with the last one because I think it's sort of the meatiest, and I want to make sure that it gets the time that it deserves. So what we did to cut the cost of this model quite significantly was actually change our strategy for how we are handling late arriving data. And I want to start briefly with a little bit of background first. So I want to talk about 2 different incremental strategies that are available in DBT. So if in your config you do not specify a unique key, you just say something like config materialized incremental, then DBT will default to using an append incremental strategy, which actually gets, in Snowflake, it would use an insert command to just take all of the brand new rows and toss them on the bottom of the existing table. On the other hand, if you specify a unique key, so you say like unique key, my primary key, whatever it is, even without you saying a specific incremental strategy, DBT will automatically interpret that as you want to use a merge incremental strategy, and it calls a Snowflake merge command, which will then perform an upsert. So basically, if the new incoming row has the same unique key as an existing row, it's going to overwrite it. And if the new incoming row has a novel unique key we've never seen before, it's going to then insert that or append that to the bottom of the table. And the main thing I want to highlight here is that merge is actually massively more expensive than append, right? And that is because you have to compare the unique key between the new incoming rows to the existing rows. So you've got maybe these like 10 million rows that you want to add on this particular build, and then you have to look at the 35 billion existing rows and see does any of them have the same unique key. And this often then requires scanning a significant fraction of the existing table, which is probably a pretty big table. Otherwise, you wouldn't be building it incrementally, right? So where possible, you should use append instead of merge. And furthermore, I want to point out that if your upstream data never updates existing rows, like it's the case that in your source table, you are only ever adding rows, you're not changing existing rows, then you should be able to use append. And you may be like, well, when does that ever really happen? But actually, it should be the case for most of us that our biggest data sets, our sort of Kimball fact models, are just doing appends, right? It's like this person clicked this button in our clickstream data at this time. You're never going to go back and be like, oh, no, actually they clicked this other button, right? Or a transaction data. This person bought this thing at this time. Even if they return it, that gets a new transaction row, right? It's not updating an existing row. And yes, you may have some data like your smaller dimensional models, like a customer's dimension where you are updating existing rows. You're changing someone's address or something like that, but that should be a lot smaller data. So there actually should be, for like your largest data sets, you should be able to use append. Okay. And then the next thing I want to say sort of by way of background before I actually dive into what we did to make this model so much more performant is I want to talk about late arriving data. So major advantage of an incremental model is that you can process only the new data, right? So you don't have to rerun all of your transformations over all 35 billion rows on every single build of this model. You just do it on the stuff that's new. But in order to do that, you have to figure out what's new, right? Which are the rows that I have not already processed? And typically the way we do that is by comparing the values in some timestamp column in the upstream table to the greatest value we already processed for that column. It would look something like this probably, right? So you select from your upstream model, and you say, if it's incremental, I'm going to filter it so that the last modified at date, selecting rows where only the last modified at date is greater than the greatest last modified date that already exists in this incremental model, right? That's like very standard incremental logic. But if you did this, you could get into trouble if you have sort of what we call late arriving data, and I'm sure like many of you are familiar with this. It's not an uncommon problem. Specifically, what I mean is like data that doesn't land in the table in the order of the timestamp column, right? So that there may be some rows in this upstream model that actually have an earlier last modified at date than the one you already processed, but that weren't here last time you ran the model, and so you want to grab those as well. Okay. So now I can actually talk about Amplify stuff and what we did. So this was our initial late arriving data setup. We were using a timestamp that was coming from the source data itself. And we worried that this could be late by up to 2 days. And so we set up our model to do something like this, which is, again, like a very standard solution to a late arriving data problem. You say, where event timestamp is greater than, select date at day -2, max event timestamp, right? We're going to look back and process the last 2 days worth of data. But it turns out that having this 2-day look-back period is much more expensive than having no look-back period, and this is for 2 reasons, one of which I think is fairly obvious, and one of which I think is a little bit more subtle. So the first one is that you end up reprocessing the same data multiple times. And you can imagine sort of that each sort of bar here is a different DBT build of this model, like over time. And on the first run, you're going to process everything in green here, which is lag 2 days worth of data, and you're going to stop because that's all the data you have at that point. And then on the next build, you have this like maybe 2 hours later, 2 hours more worth of data, and you're going to process that, but you're also going to look back and reprocess the last 2 days worth of data. You're not going to catch this part anymore. This is sort of like a moving window where you're catching more and more new data and leaving more and more old data behind. And if you look at this, if you sort of were to slice it vertically and follow like the life cycle of a particular piece of data, you'd see that that data is getting processed in the first build, and then again in the second, and again in the third, and so on. And in our case, if we're running this 9 times a day, and we're looking back 2 days, then we are reprocessing the same data 18 times, which is a lot of times to do the same transformation on what is essentially the same data. And then the second thing that I want to call out that I think is maybe a little bit more subtle is that by reprocessing the same data multiple times, we are actually introducing duplicates into a data set where previously there were none. So this was actually some clickstream data. There were no duplicates in it upstream. There were no changes to existing rows. Theoretically, we should be able to do append and just grab the new rows and stick them on the bottom, except now, because we've reprocessed some data, this batch contains a lot of unique keys that already existed in this batch, and so we have to specify a unique key so we don't get duplicates when we add them to the model. Okay, so how do we solve these problems? I'm going to talk about this actually in 2 pieces. So the first thing we did was to change the timestamp that we're looking at. So rather than using a timestamp from the external source data, like an event timestamp or a last modified at or something like that, we now have switched to, for all of our incremental models, we always use a timestamp from the ingestion itself, right? So in this case, Snowpipe start scan time, or a 5-trans synced at, or we do some batch loads where we actually make sure that when we load that data that we put a timestamp on it that is like an ingested at timestamp. And what this does is it dramatically cuts the amount of time by which data can be late, right? In fact, in some cases, it cuts it to 0, right? If you're doing like a batch load and you put a timestamp on that, that is the time that the data landed in your table. There is no possibility that the data could come after you said it got there because you're timestamping when it got there. But in this case, actually, for Snowpipe, and this 5-tran has this same problem as well. It turns out that it can still be a little bit out of order, the timestamps. Specifically, Snowpipe only offers you this start scan time. It would be really nice if they offered an end scan time, but they don't. So they offer this start scan time, which tells you when it started scanning the file. And so there is a little bit of lateness still in that some files can start scanning earlier, but actually land in the table later than a file that started later. But we've done some extensive testing on the data in this particular model, and we found that in this particular data set, no file ever takes more than 30 seconds to process. And we actually continually test that. We actually caught like a weird bug that Snowflake had a couple months back with their Snowpipe because of that, where we said, oh my God, all of a sudden, files are taking 3 minutes to load. What happened? And they didn't know until we told them. In this particular data set, no file ever takes more than 30 seconds to process. So that's sort of our outside limit for how late the data can be. So we set a very generous look-back period of 5 minutes. We said like it's not possible for it to be any more than that late. And so now, we can sort of update our pattern to only look back 5 minutes. So you would process this on your first like full refresh, you'd get everything, and then 2 hours later you're gonna process the new data plus the last 5 minutes, and then again, the new data plus the last 5 minutes. And this is a lot better than what we were doing before, because now you're only reprocessing some data actually only once, right? Like what's right here only gets processed once, and then some data you're still processing twice, but way, way better than 18 times. But unfortunately, this still has the same problem of you are introducing duplicates where previously there were none, right? So this little bit of data here is processed in this batch, and it's also processed in this batch, and so you still have to use a merge. So the next thing we did is we actually decided to sort of flip this problem on its head. And instead of reprocessing the last 5 minutes worth of data, what we do now is on every run, we process everything but the last 5 minutes worth of data. And so what that means is, like, for example, on the first run, we're going to process everything up to here, and then we're going to stop and not catch that last 5 minutes, right? And if you think about it, this is us saying, like, everything that has a start scan timestamp of 5 minutes ago or older, we think for sure is in our table right now, right? There is no way that there is something like hanging out there in limbo with a timestamp that is 5 minutes ago or older, and it's going to come to our table later. It's not going to be there now, right? And so we skip that data on the first run, and then on the second run, we can say, we are sure that we got everything in here. We didn't miss anything. There's no late arriving data in there. And we can pick up exactly from where we left off and start processing from there forwards. And then we, again, skip the last 5 minutes. And this now allows us to switch from using a merge strategy to using an append strategy, because there are no duplicates, right? There is no data that is processed twice. Everything we know for sure is like a unique new row. And we have tests on this to ensure that that's the case, and it does in fact work, and it is in fact the case that we are not introducing duplicates in this way. What this actually looks like in our code is we say, where start scan time is, less than 5 minutes before the current time when this model is being built. And notice that that is outside of the incremental logic, so that is on every run, including a full refresh. And then, if is incremental, we can say, and start scan time is greater than just the greatest one we ever processed, and we don't need any look back period. And by making just these two changes that I talked about now, we were able to get the cost of this model from $50,000 a year down to just $600 a year, so about 100x improvement in the cost of this model. Okay, so that is that piece. I'm going to talk about another thing now. But that was a lot of talking. Sorry, I have a lot of fun stuff to tell you and not a lot of time, so I'm talking kind of fast, but it gets to be a lot. Okay, the next thing I'm going to tell you guys is about conditional warehouse sizing. This one's like a little bit more straightforward. In dbt, it allows you to specify a particular Snowflake warehouse on which to run your model. You could do something like in the config block, Snowflake warehouse equals, and then whatever the name of your warehouse is. But the problem is that in DBT, natively, you can only specify one warehouse per model, which means either you're going to pick like a very big warehouse that's appropriately sized for your full refreshes, which means then on all your incremental builds, you're just like wasting a bunch of resources that you're not actually using, or you're going to pick a very small warehouse that's more appropriately sized for your incremental builds, and then when you fully refresh it, it takes like 12 hours, which is also not ideal. So what we did actually was add a macro to our project, which we call swap warehouse, and it runs a very, very simple SQL statement that says use warehouse and whatever warehouse name you pass into the macro. And then we call that in our incremental model. So this is the, like what it looks like before. I just have this up again so you can notice the difference. And then this is what it looks like now. And I want to call out two differences. So one is that we removed that Snowflake warehouse argument from the config, and that's really important. If you leave that in, it will actually override this. So make sure you take that out. And then what we do here is we actually use the same sort of is_incremental function that's available, for your regular incremental logic. And we say if it's incremental, and then we call our swap warehouse macro, and we specify the warehouse we want to use on an incremental build, else, and then we specify the warehouse we want to use on a full refresh. And so that works. We've been doing it for about a year and a half now without any issues. So we're pretty excited.
Does it auto turn off? Do you have that setting on the Snowflake side where it just auto turns off?
Auto suspends? Yeah.
Yeah, auto suspends.
Yeah, that's a good question. OK, last but not least, I want to talk about unique tests for large incremental models, because this can also be an issue. Two things sort of about unique tests on large incremental models. One is that they are going to run over all of the rows, which is a lot. And two is that typically in DBT, you actually cannot change the warehouse size on the test, right? So even if your model is running on like an extra large or 2XL or whatever, the test is going to run on whatever your default project-wide warehouse is, which in our case is an extra small. So you've got now your test on this very small warehouse on this very big model, and it's doing it over all of the rows. So how do we solve this? We actually think that there are sort of three different patterns that we use on different incremental models to solve this. The first one is sort of the simplest, and it's if we want to only check uniqueness for the new incoming data. So basically, like make our test incremental, just like our model is incremental, right? So just check the new 10 million rows or whatever it is that we added, and make sure that they are unique amongst themselves and not compare them against the existing rows. This is very simple to do. You can simply use, DBT, lots of Snowflake DBT. You can use DBT's built-in where clause. And so for us, this looks something like this. In the model itself, we'll add a column that just pulls the timestamp for when that row was actually created. This will be put sort of in batch on all of the rows created as a single DBT run or build of that model. And then in the YAML file, we just call the unique test the same way you normally would, and then config where. And then we say where this row built at was basically within the last hour. The lag there is really just the time between when the model was built and when the test runs, which should be very, very short, but we put an hour just to be generous. In the next part, I'm actually going to talk to you about a little bit more complicated but more robust way of limiting it to the last batch of data that was added. One thing to note just here is to be really careful in responding to failures for this test. So if this test fails on a run and then it passes on a subsequent run, then that does not necessarily mean that your problem is solved, right? Because you're only checking the new rows for uniqueness. It could still be the case that there were duplicates in the previous batch. So just something to call out. The second thing is sometimes you might want to, and we actually use this one more often, check uniqueness for the new incoming data plus a certain number of prior loads. So maybe, for example, you've done this very aggressive thing that I just told you about, where you have removed the unique key from your config, and you are just appending new rows, and you are worried that maybe somehow that logic is not working out exactly quite right, and you might be duplicating rows from one batch to the next, for example. And so you might want to check the new incoming batch plus just the batch before it. Or maybe there's something about your ingestion, about your data generating process that you think maybe like this batch plus the 2 or 3 batches before it might have duplicates in them. So what we've done for this is we actually created a custom test that is designed just for this purpose. What we do is In the model itself, we add a batch ID column that works as follows. So it has a value of 0 for all rows that are added as part of a full refresh. And then the value just increments by 1 for each subsequent incremental build. So this is what this really looks like on the model that I've been talking about today. So the last time we fully refreshed this, there were 35 billion rows in it, and those all got a batch ID of 0. Then you can see the next build after that, there were 3 million rows, and those all got a batch ID of 1, and so on, right? So each new batch that was added to the model, those all got a batch ID added to them. The code to do that looks like this. I'm not going to walk you through it in the interest of time, but it is here in the slides. Feel free to take a picture of it. Lots of people already are, or to check it out in the slides afterwards or in the recording. And then step 2 is we create a custom test that basically pulls the rows from the current batch plus the prior n batches, where n is an argument that the user can specify. Like you can say, give me just this batch and 0 prior batches, so I only want to check this one. This is what I'm saying. This is a little bit more robust way of doing what I was talking about in number 1, where you check only the new data. Or you can say, give me this one and the prior 1 batch, or this one and the prior 2 batches, and so on. And it's just going to check uniqueness across those rows that you pulled. The code for that test looks like that. So that one's a little bit complicated. I'm not sure if it's going to show up in your pictures, but it is here in the slides if you want to take a look at it after. And then what we do is in the model's YAML file. We call this test. This part's much simpler than writing the test in the first place. And our test is called Unique Incremental. And all you do is you specify a number of batches argument. And this test is also set up actually to use our swap warehouse macro so that if the batches you are pulling includes that 0 batch, so if you're pulling like 0, 1, 2 or 0, 1 or whatever, if you include the 0, then it will use the full refresh warehouse that you specify. And if you are not including the 0 batch, then it assumes that these are all much smaller, and it will use the incremental warehouse that you specify. Last but not least, suppose that what you really think is super important is to check uniqueness across the entire data set. So you're going to check all of the rows in your data set for uniqueness. In that case, we have a custom test for that too. Lots of custom everything. And we are just going to turn up the warehouse size on the test. And we're going to run this test on a bigger warehouse because this is really important to us for whatever reason. So we create a custom test that runs a swap warehouse macro before executing the test. The code for that one is much more straightforward. And then in the model's YAML file, you can call that test. It's just called unique custom warehouse and specify the warehouse name. Last but not least, I want to just make a brief note about not null tests. So we actually don't do anything special for our not null tests. And if you think about that, it is actually the case that we only want to check not nullness on the new incoming rows, right? Like you'd think you'd be like, why wouldn't you do the same thing you do for uniqueness where you just limit it to the most recent batch, right? Like, why check not nullness across everything? Because not nullness especially, it should be that only the new stuff could be null. The old stuff, you already checked if it was null, so it shouldn't have suddenly become null magically somehow. But we actually found that in Snowflake, not null tests tend to be faster without a where clause. And this is because you can see it in the query plan. Snowflake is returning a metadata-based result if you don't include that where clause. So when you include the where clause, it actually tries to go look at the data. But if you don't, it just sort of looks at the metadata it has about the table, and it says, yeah, none of the rows in this column are null. And then lately, actually, we've been preferring to use model contracts and to add a not null constraint instead of using a not null test. And what this will do is it will actually prevent the model from building in the first place if any value in that column is null, rather than a not null test, which is going to allow your model to build with the null values in it, and then only afterwards let you know that there's a problem with it. So that is that. That is it. I went very fast there. Thank you all so much. I'm Dina. I will take questions in a minute. I spend lots of time thinking about incremental models and have lots of other fun things to say about them. We actually have 2 custom incremental strategies that we've written. We also are thinking really carefully about how you do incremental models with joins, but I had to talk super fast just to get all of that to fit into 30 minutes. But if you want to hear more about other incremental model stuff that we are doing, please feel free to reach out to me on DBT Community Slack or LinkedIn, and I'm happy to chat with you about incremental models or about anything else that you want to chat about related to DBT. It's not. It should be. That's a good point. Yeah. Yeah. Just swap warehouse itself, right? There was probably a faster way to get there. That one. Any other questions? Yeah.
So you mentioned that you were able to, with basic incremental models, you were able to reduce it from like $3 million annual kind of spend to 50,000. Was there another reduction that needs to be
Yeah. From full refreshed incremental would go from 3 million to 50,000. We never actually did it the 3 million way, but that was my calculation, sort of based on what a full refresh costs. And then from the 50,000 to adding these two things, we got it down to $600 a year. So, yeah. A little bit. I wanted to use them for a particular use case where I think incremental models are not great at joins. And I wanted to use it for that, and I found that in that case, it just wanted to fully refresh it every single time, which I was not happy about. So I kind of abandoned them after that, but I should take a look at them again. Yeah.
Do you feel like there's an ethos or like some sort of internal threshold you have about like when all of this work is worth doing versus not worth doing, or is it just like financial?
Yeah, I think it's a good question. I don't know. I think it's probably, like in this case, we had big enough data that it was worth it. But certainly on small models, like even sometimes on small models, I don't necessarily think it's worth making them incremental, especially if you're going to have to use a merge strategy. It can end up being more expensive than fully refreshing it sometimes. If you can use append, it's always better than a full refresh. Like it's basically free. But if you're going to use merge, it actually can end up being more expensive for little models. So.
Interesting about snowpipes and the scan data.
Yeah.
You build snowpipes and use insert timestamp as like.
Yeah, I've looked at, so we tried to do that too, and it looked the same as the snowpipe start scan time. Yeah. They weren't the same, but they had the same issues. Like I was comparing them against, yeah, that's a good question. Yeah.
I've seen that has historically been the closest. Again, we don't have that issue. We don't have like these like little miniature buckets.
Yeah. No, in the next plot you process from wherever you left off before up until not the last 5 minutes from like that time. So for example, if I was to build the model at 1 o'clock, I would process everything from the whole day up until 12:55. And then if I was to build it again at 3 o'clock, I would process everything from 12:55 to 2:55, right? But always like not 5 minutes, not the last 5 minutes before whenever I'm building it. Exactly. Yeah.
Incremental processing, like for all the batches, or if you don't have that use case, if you can reprocess it. So,
Like a full refresh or?
something like that, or let's say batch 10 to 15 was bad.
Yeah, that's an interesting question. We don't have a setup for that yet, but it's a good question. Yeah.
Have you considered creating it in a merge strategy?
Say it again.
If you would have created,
Incremental predicates. Is that what you said?
no, if you created this incremental model in a merge strategy,
Yeah.
and then the merge strategy will take care of the uniqueness by itself, and you will have less unique checks than here, because
Uh,
a bunch of data, and if you have like a cluster of the unique checks, you will not scan everything.
So you mean instead of a unique test? So if in your first full refresh you have duplicates and you don't check that, then in your next load, if you have, you're only going to pick up those duplicates if the thing you're trying to merge in is also a duplicate of the already pre-existing duplicates.